Bismillahirrahmanirrahim. Welcome to the Electrical Engineering channel. In this lecture, I am going to demonstrate the speed control methods of an induction motor. The speed control of an induction motor can be achieved by changing the number of poles, changing the line frequency, changing the line voltage, and changing the rotor resistance. The first method of controlling the speed is changing the number of poles. We know that the synchronous speed of an induction motor is equal to 120 times F over P. If we increase the number of poles, the synchronous speed will decrease and vice versa. So when we change the synchronous speed, it will directly change the mechanical speed of the rotor, and greater than smaller the number of poles, higher will be the synchronous speed and higher will be the rotor mechanical speed. The control of speed can be achieved by changing the number of poles in this sophisticated manner. So in this circuit, you can see there are two current loops. This is the first loop and this is the second loop. And the connection of these windings is done in such a way that the direction of current in this loop is anti-clockwise and the direction of current in this loop is clockwise. As a result, this loop will correspond to a north pole and this loop will correspond to a south pole because the direction of current in both the loops is opposite. Now, if we talk about the cross-sectional view of the stator of the induction motor, we will have such slots in the inner periphery of the stator. So this is the side A1 and this is the side A1 dash. Here the downward arrow or the downward direction of current corresponds to the direction of current into out of the paper. So downward direction corresponds to direction of the current out of the paper in this figure, and the direction of current upward corresponds to the current flowing into the paper in this case. So A1 corresponds to, since the direction of current is downward, so in this figure the current will be flowing out of the paper, and for this A1 dash the current will be flowing into the paper. So if we apply the right hand rule to get the direction of magnetic field, the direction of magnetic field will be indicated by the thumb and it will be downward. So the magnetic field lines are originating from these two loops or this side, so it will become a north pole. Now if we analyze this direction of the current, then we will see that in A2 the direction of current is upward, so it will be flowing into the paper, and the current for A2 dash will be flowing out of the paper, and the direction of flux will be downward. And here we can see that the magnetic field lines are terminating at this side. So this will be a north pole and this will be a south pole. So this is a two-pole stator. Now, if I reverse the connections at this side, so that I get the anti-clockwise current direction for one loop and anti-clockwise current direction for the second loop, then I will have a four-pole stator. Now, how will it be possible? So you can see here the arrangement is changed and the direction of current is anti-clockwise for this loop, and this current will be flowing from this loop to this loop, and again the direction of current will be anti-clockwise. So this current loop will correspond to a north pole, and this current loop will also correspond to a north pole. Whenever there are two north poles, there will be analogous south poles in the stator because we cannot isolate magnetic poles from each other and we cannot generate only the north poles or the south poles. So whenever there are two north poles, there will be analogous two south poles. So in total, there will be four poles in this case. So the similar understanding can be developed for this direction of the current uh, in this cross-sectional view of the stator. So this will be a north pole. Magnetic field lines will be originating from this point, and they will also be originating from this point, and they will be terminating somewhere here. So this is a four-pole stator. So if we double the number of poles using this mechanism, we can halve the synchronous speed, and we can also reduce the mechanical speed of the rotor. So this was the first method. The second method is changing the line frequency. So the effect of changing the line frequency can be observed by analyzing the torque speed characteristics of the induction motor. So torque speed characteristics of this induction motor are already discussed in the previous lectures, and this is the mathematical model of the induction motor, and we can uh, draw or we can plot the torque of induction motor at two different frequencies. So this is the complete code, and you can type this code by yourself, and when I run this code I get such a result over here. So in this figure I have considered two different frequencies, the operating frequencies. First operating frequency is 40 hertz, second operating frequency is 60 hertz. So when I choose 40 hertz frequency, line frequency, or the frequency of the applied voltage, I get such a torque speed profile. So in this case, the maximum torque is greater and the starting torque is also high, but the speed is smaller. And in this case, I have smaller starting torque, I have smaller pull out or maximum torque, but the speed has increased considerably. So this is the torque speed curve of an induction motor at different frequencies, and at other frequencies we can have such a profile. So this profile clearly indicates that if we operate the induction motor at higher frequency, the speed will be high, but the torque will be less. Either it is a starting torque or a pull-out torque. The third method of changing the speed is the changing of a line voltage. So again, I can analyze the torque speed characteristics of the induction motor, and I can choose two different line voltages for plotting these characteristics. So in the first case, the phase voltage is 460 volts, and I have chosen phase voltage as 360 volt for the second case. And when I run this code, I get such a profile. And in this case, by increasing the line voltage, the starting torque is increased at 460 volts. The pull-out torque has also increased, and for smaller voltages, this maximum torque is small, and the starting torque is also small. So at higher voltage, the torque will be high, and we know that whenever torque is high, the speed will also be high. So this is how we can write the code. So this code can be written by yourself very easily, and we can also analyze the values of pull-out torques and the starting torque. So at in these lines, I have not put any semicolon. So when I run this code, these values will be calculated and printed in the command window. So the fourth and final method is changing the rotor resistance to vary the speed of the induction motor. So when we have a smaller resistance, this is the first profile. For the RB, which is greater than RA, the profile will be like this. And we know that here we have torque and here we have speed. The maximum torque is same for all values of rotor resistances, but the starting torque is changing. And for a smaller value of rotor resistance, the starting torque will be minimum, and it will go on increasing as we increase the rotor resistance. But the maximum torque is same, but the position for the maximum torque is different. So here, for smaller value of rotor resistance, the maximum torque is actually corresponding to the higher speed. And for RB, the maximum torque value is same, but it is appearing for smaller speed values. So it clearly indicates that when I increase the rotor resistance, the speed of the rotor actually decreases. The starting torque is increased, but the speed of the motor is decreasing. So this is another method of which varying the rotor resistance and to vary the speed of the induction motor. And we can also check the code of this file, and when I run this file I get such a profile. So the maximum torque value is same, but the starting torques are different, and the speed values corresponding to the pull out torques are also different. So this is another code which can be written very easily by yourself, that is all about the speed control methods of the induction motor. Now I am going to discuss the star delta switch. Star delta switch is actually also a relevant topic which deals with the speed and torque of an induction motor. So in star delta switch, what actually we have to do is we should connect the stator of the induction motor in star mode at the start when the motor is at rest. So when the motor is at rest and we want to just run the motor, we have to connect the stator windings in the star connection. When the motor comes to the running mode, the stator windings should be converted to the delta connection or delta mode. So this is the purpose of a star delta switch, and the purpose of doing this transition is to keep smaller current, smaller winding current at the start and higher current at the running condition. So if we analyze these characteristics, we can see that at the running condition, the torque is high, but at the starting condition, the torque required is less. So in the star connection, we will see that the motor draws actually three times smaller current, and it will also require three times smaller torque at the start condition, and that smaller torque and smaller current will be presented by the star connection. When the motor runs or when the motor is in the running mode, we will connect the windings in the delta connection to get higher torque, higher running torque, and higher current. So this can be achieved by making such an arrangement, and here we can see that these are the three phase stator windings. This is the first phase A1 A2, and this is the second phase B1 B2, and this is the third phase C1 C2, and this is the rotor which is separate. It is actually electrically isolated from the stator. In the start condition, here we have a switch, and this switch is called a triple pole double throw because it has three terminals. So it is a triple pole, and double throw means it has two possible positions. Either it will be in the open condition or it will be in the closed condition. So this is a triple pole double throw TPDT type of switch. So in the start condition, this switch must be opened, and when this switch is open, these three windings will be connected in star mode. So this is the first phase A1, and this is A1, and this is the second terminal of this winding, which is A2. Similarly, this is B1, and this is B2, and this is C1, and this is C2. They are all three windings are isolated from each other, and at this point we can connect all these three windings A2, B2, and C2. Then it will become a star connection. So when we are in the running condition, we have to close this switch. So when we close this switch, this A1 winding will be actually connected with B2. So A1 will be connected with B2, and B1 will be connected with C2. So this is B1, and it will be connected with C2, and this C1 will be connected to A2. So this is A2, and this will become a delta mode. So these windings of the motor will be connected in delta configuration when we close this switch. So this is how we can change the connection of the stator in the starting condition and in the running condition. So this is a very simple mathematics to illustrate the magnitude of current and the magnitude of torque in delta connection and in the star connection. So here we have V1 is the phase voltage and VL is the line voltage. So phase current in star connection, Y connection is also called a star connection, and this is the phase current which is represented by this P, and ST means this is a starting current. So starting current of the motor in star connection and phase or starting phase current of the motor in star mode is equal to phase voltage divided by impedance. So this is phase voltage and this is the impedance. And in star connection or Y connection, phase voltage is equal to line voltage divided by square root 3. So on the other hand, the phase current in delta connection at the start is equal to phase voltage divided by the impedance. And in delta connection, phase voltage is equal to the line voltage, so it will be line voltage divided by the impedance. So in delta connection, the line current will be equal to square root 3 times the phase current, and we will have under root 3 into VL divided by ZE10. So VL divided by ZE10 is actually equal to I star delta P. So I star delta P is equal to VL divided by ZE10. And in star connection, the phase current is equal to the line current. So the phase current is equal to the line current, and line current is equal to line voltage divided by square root 3 times impedance. So now the starting line current using a star delta switch divided by starting line current in delta mode is equal to starting phase current or line current. They will be same in star connection divided by starting current in delta connection. So this is actually delta L. So this is a line current in delta mode. So this is VL divided by square root 3 into impedance. This expression is taken from this equation, and this expression square root 3 into VL divided by impedance, this is taken from this expression, and all the terms VL will be cancelled out with VL, ZE10 will be cancelled out with the ZE10, and we will have 1 by square root 3 multiplied by square root 3, so it will be equal to 1 over under root 3. So the line current in star connection is equal to 1 by 3 times line current in delta connection. So the starting torque is actually directly proportional to the current. So starting torque for a star delta connection divided by starting torque in a delta connection will also be equal to 1 by 3, because the torque is directly proportional to the current. On the other hand, the torque is proportional to the square of the voltage. So if we consider this relationship, then we can see that starting torque in Y connection is equal to line voltage divided by square root 3. This is the phase voltage in star connection divided by starting torque in delta connection. So this is also phase voltage. So phase voltage in delta connection is equal to the line voltage, and phase voltage in star connection is equal to line voltage divided by square root 3. Since the torque is proportional to the square of the voltage, so it will be square and it will also be square, and VL square divided by VL square will be cancelled out, and we will have 1 by 3. So from both the expressions, the starting torque in a star connection will be 1 by 3 times of the starting torque in delta connection, and due to this smaller torque, there will be smaller current which will be drawn by the motor at start. And at the start, since the motor is at rest, its rotor is not rotating, so it should draw less current because there is no back EMF. So if the motor is drawing a high huge amount of current, since there is no back EMF, the current can exceed and it can damage the stator windings. So that is all about the star delta switch, and the star and delta connections in a three-phase winding can be achieved by considering one terminal of the three windings, and we can short circuit that terminal, each terminal of the three windings, so they can be shorted, and the other terminals, they will be connected with the three phases. So this is the first phase, this is the second phase, and this is the third phase, and the second terminal of all these three phases will be connected with each other. So this will become a common point, W2, V2, and U2, and this will be the common point, and these 3 points will correspond to the three phases. But in delta connection, W2 will be connected with U1, U2 will be connected with V1, and V2 will be connected with W1. And we will have three connections from three different positions. So such a connection will give us the delta connection. So this is U1, this is U2, this is one winding, and we will connect W2 with U1, and we will connect U2 with V1, and here we have the third winding. This is V1, this is V2. So V1 will be, U2 will be connected with V1, and V2 will be connected with W1. So this will become a delta connection. So that is all about our today's lecture of speed control of an induction motor, and I hope you have enjoyed and understood the concepts which are discussed in this video. For watching more similar videos, please stay tuned to this YouTube channel. Until the next lecture, it's goodbye.